Babies, welcome. Section 6.3. What we're going to be talking about in this section is looking at the differences and similarities, I suppose, between linear functions and exponential functions. Both of these, again, linear functions is stuff, functions we spent a lot of time on. Exponential functions, what we're talking about here in Chapter 6. So we're going to compare them because they are very similar, and you're going to see some differences, obviously, but we're going to see some similarities between the two. So obviously, graphing wise, we spent some time graphing. A linear function is obviously, when you graph it, going to form a straight continuous line, as we can see here. Okay, continuous meaning that it's going to go, in this case, up and to the right at a constant rate and continue to go on and on and on and on forever, making it a straight line. And then for an exponential function, we're going to see that curve. Okay, so it's going to curve upward, which would represent exponential growth, and we could see the opposite where it curves downward, where it'd be exponential decay. So we've talked about those things. So graphing wise, linear function is always going to form a straight line. Exponential function is going to form some sort of curve, whether it's curving up or down. So we can see a difference between the graph of the two things. Obviously, a line versus a curve is a huge difference. We've also spent some time on the formulas for both linear and exponential functions. So for a linear function, we spent a lot of time on what's called slope-intercept form, where the two ingredients you were given in this formula was m, which is the slope, and for a line, the slope represents, given any 2 points, the rise versus the run of that line. So how far it goes up or down versus how far it goes over. And then we were also given the b value, which is called our y-intercept. And the y-intercept, think about it as the starting point of our graph. I always like to view it as the y-axis cuts our graph into the left and right, cuts it right in half. So b is going to give you that middle value of where the line crosses. There is also an x-intercept, but when we graph this function, we're going to use b. Now, this is very similar to an exponential function. Now, an exponential function, looks similar, looks different. We have a times b to the x, but when we think about the values of a and b, they are very similar to a linear function. So, for example, the b value. So the b value represents the multiplier, and this is kind of what we dealt with exponential growth and decay, that if that b value were bigger than 1, we would see that a graph would be, the function would be growing like we have here. But if I had a b value that was less than 1, between 0 and 1, we would see a decay graph where it actually gets smaller. And again, it could be above or below the x-axis depending on whether we have a positive or negative value there. Okay, but the b was representing that multiplier. So think of b as being very similar to the slope. Okay, this is one thing we are going to focus on, is we're going to compare the slope of a line to that multiplier in an exponential function. And then we have our a value, and our a value is like our initial value. Okay, so that represents on the graph the point here where my exponential function is going to cross the y-axis. All right, and that is very similar to the b value, our y-intercept. In fact, our y-intercept in slope-intercept form is essentially the y-intercept in our exponential function. So we see some common themes here with, that initial value or that starting point for a linear exponential function. And then we have the slope and that multiplier, which is going to represent how things are changing within our line or within our curve. So our goal within this section is we're going to look at points. If I were to give you points, what would that look like on a graph? Would it be linear or would it be exponential? We're going to look at then table of values. We can compare the equations, but we're going to use these things to try and model the differences between linear and exponential functions. All right, in this first example, we're just going to look at the graph of a set of points and determine whether it's a linear function, exponential, or neither. Linear, obviously, we're going to see a straight continuous line once we plot the points. Exponential, we're going to see a curve up or down depending on its growth or decay. And again, it's going to be continuous. And then neither would be some sort of other function that is not a line nor a curve. So first thing we got to do is let's plot our points here in our very first example. All right, we should get these sets of points. Now, when we plot the points in, we can kind of recognize the shape that it's going to form. So if I were to just connect here, and I'll use my arrows to show, what we're getting is a kind of a V, an upside down V-shaped graph. All right, so what I want to know is this linear, exponential, or neither? So when we look at this, yes, I do see that both sides of this V are straight lines, right? However, if it wants to be a linear function, we need to see a continuous line throughout. That means it would continue in the same direction over and over. So here, as it bends back down and starts to reverse direction, instead of going up, it goes down, this would make it not linear. And since it's not a curve up or down, this would not be exponential, so that means this graph here would be neither. It's going to be some other graph or some other function that we haven't studied yet. Same thing in example 2. So let's plot our points, which should give us this shape here. All right, now if I were to connect these points, in order to do that, I would need to connect them with a nice, smooth, continuous line. So based on this graph, we can see that this would be a linear function. Linear because it forms a straight, continuous line. All right, same thing in our third example. We're going to plot these points. There's one mistake. This one came out as 212, but it should be 1/2. But nevertheless, we're going to plot our points to see what sort of shape we should get here. All right, so plotting my points, here's what I get. So if I were to connect these, obviously to form this shape, I would have to draw it using a nice, smooth, continuous curve, which would mean that this function is going to be exponential. So these 3 examples, pretty simple. Our goal is to just plot the points, and graphically a linear function is going to be a straight line. An exponential function, we're going to see some sort of curve up or down. In this case, we have a curve downwards, so this would technically be exponential. And if I wanted to get super sassy with it, I would say exponential decay. All right, so in this next example, we're going to look at trying to determine whether a function is linear or exponential, but looking at a table of values. And then in the second part, we're going to write our function, whether it's linear or exponential. So the key thing here is that we're going to look at the change between the values, what's called the rate of change. All right, so know that our x values are always going to represent what's called the inputs, and our y value is always going to be considered our outputs. To determine whether a function is linear or exponential, what we're going to look at is we're specifically going to look at the outputs, okay? Now, as I do that, I want to make sure that my inputs, my x values, are going up by a constant rate. So notice my x values here in this first table are going up 1 every single time, okay? Now, why we're not going to look at the inputs is because I can choose whatever inputs I want. But what we do then is we recognize the pattern between the outputs. So my outputs, I have 9, 5, 1, -3, and -7. So my goal is to try and figure out what is the pattern going on between those numbers. I will notice here that from 9 to 5 means it goes down 4. 5 to 1, it goes down 4. 1 to -3 goes down 4. And same thing for the last 2 points, it goes down 4. So notice how it's going down 4 every single time. So it has a constant rate of change. Because that rate of change is constant, that is going to make this function linear. Okay, now our second goal is we're going to write the equation of this line using our function of our slope-intercept form. Okay, so again, what we're going to plug into this function, and we've practiced doing this before, is we're going to plug in a number for our slope and our intercept. Okay. Now the nice thing here is that our slope is the rate of change. So notice that it was going down 4 every single time. So when I write this equation or this formula, my m, which is my slope, is going to be the -4. It went down 4 every single time. I'm going to multiply that by x, and then my goal is to add my y-intercept. Now, the question is, how do you find your y-intercept from a table of values? So your y-intercept is always going to be, like on a graph, the point where the line crosses, or your function crosses the y-axis. All right, now in a table of values, it's going to be a little bit more difficult to understand. So our y-intercept, if we think about where, let's say, it crosses a graph right here, our y-intercept b is always going to be a value where x equals 0, and then we have that b value, that whatever that y value is going to be. So the key thing is we got to figure out, when does x equal 0? So on my table, I will see smack dab in the middle here that when x is 0, I have a y value of 1. That means that my y-intercept is going to be 1. So in my function, I'm going to write +1 at the end. And in slope-intercept form, I get my complete function of -4x plus 1, where -4 was my slope, went down 4 every single time, and +1 was my y-intercept, where x equals 0, what was the value of y. All right, we're going to do the same thing for our next table. All right, so again, our x values for our inputs, we're going to see just like the last one, they're going up 1 every single time, okay? Now, again, I can choose whatever inputs I want, so that x values are not really going to tell me too much about the function, but what I want to look at, again, are my outputs, my y value. So notice here I go from 1/3 to 1, 3, 9, and 27. What I want to do is recognize the pattern there. So notice that this is not addition or subtraction, but instead it is multiplication. I will see that it's times 3 every single time. Now, I know it might have been a challenge to understand the 1/3 times 3, which would give you 1 because we're dealing with a fraction, but 1 times 3 would give you 3, 3 times 3 would give you 9, and so on and so on. So because we are multiplying by a common number, that means this function is going to be exponential. Now our goal, understanding that it's exponential, is to now write its formula. Okay, so again, for all exponential functions, they're going to be of the form a times b to the x. Now remember, a, kind of like I talked about before, is our initial value. Think of a as my y-intercept. Okay, so it's going to be the same thing up here. So in my table, my a value is going to be the value when x is equal to 0. Okay, so we'd have 0 and then comma a in this case. So I don't want to confuse you, they're both the same thing. The y-intercept for a linear function is our a value for an exponential function. So on my table, I want to identify where x equals 0, which I can see right here, which means that my a value is going to be 9. So I'm going to plug in first y equals 9, and then in parentheses, b is going to be my multiplier. So notice I'm multiplying by 3 every single time. So 3 is going to go inside the parentheses, and then I would write x again as my exponent. All right, so what did we have to do in writing these functions? Well, first of all, we had to first figure out the rate of change. Notice for a linear function, we subtracted 4 every time. So for a linear, we'll always see, for its rate of change, addition or subtraction. For an exponential function, we saw multiplication, or we can see the opposite, which is division, okay? Or it could be multiplying by a fraction, which is technically the same thing. All right, so we had to identify our rate of change, and then notice the kind of commonalities in how we wrote our function. For a linear function, we found our rate of change, which is called our slope. Okay, for a exponential function, we found our rate of change, which was our multiplier, b. All right, and then we also had to define our starting point, which for a linear function is our y-intercept. Our initial value for an exponential function is technically our y-intercept as well. So we had to find the value of y when x equals 0. All right, so as we saw in the last example in the table of values, the big difference between a linear function and an exponential function is that rate of change. For a linear function, we're going to see a constant addition or subtraction, means it's going to go up or down by the same amount every time, which is why a linear function is going to form a straight line. An exponential function, if we were to do addition and subtraction, we're going to see that it's actually going to increase, okay? So a linear function, we form a straight line because that rate of change is constant. Whereas for an exponential function, we're going to see it grow bigger and bigger and bigger every time. So when we look at the rate of change, think of rate of change as just simply our slope. What we can do is we can compare these two things. Knowing, again, the idea of slope is just simply the rise over the run. The rise is our change in our y value, and the run is our change in our x values. So if I wanted to compare these two things, think for a graph, all I got to do is just like finding slope, I got to find 2 points. In this case, if I find 2 points that lie on the line, and those same 2 points that lie in the exponential function, what I can do is actually compare these two things. Now here's the only difference is that when we have an exponential function, depending on whether it's growth or decay, is that for a linear function, it's always going to grow by the same amount every time. But for an exponential function, if it's, let's say, exponential growth like we have here in our picture, that once we exceed that point, know that this thing is going to grow at a much bigger rate than what we would see for the line. So we can compare them over a given interval, but then beyond that interval, we're going to have to understand whether the exponential function is growing, getting bigger, or whether it's getting smaller, whereas a line will always go up by the same amount every single time. All right, so we're going to do just that in this example. So we're going to compare two essentially websites here. We're looking at publicly traded websites that are now accepting new members, and we're going to try and figure out or kind of compare these two websites. Our goal is to kind of see and visualize the difference between a linear function and an exponential function in terms of that rate of change. All right, so on the left side, we have the table of values for website A. Obviously, you can see the days that we have here are X values and our members and the Y values, and we have the graph for website B. So obviously with the graph, easy to see we have a curve. So because we have a curve, we know right away that that is going to be an exponential function, okay? Now, for the table of values, a little bit more difficult, but we did look at how to find, whether it's linear or exponential from a table of values. So if I were to compare these points, I'll see that they're getting bigger. If I look at, let's say, 650 to 1,025, obviously I'm going to have to, let's say, add a value. So if I were to figure that out, I would add 375 to get to that number. Now, if I add 375 again, I would get to 1,400. And if I continue to add 375, what I'm going to do is I'm always going to get that same or that exact value afterwards. So because I'm going up, I'm adding the same amount every time. This table of values is going to represent a linear function. So in website A is going to be represented as a linear function, and website B is going to represent an exponential function. So our goal is to compare the rates of change of both these websites. So it says that we are going to compare the rate of change over the same time interval from day 10 to day 20. So on our table, here's day 10, here's day 20. On our graph, we're going to have to identify, okay, here's day 10, here's day 20. We probably have to estimate some values there. And what we're going to do is look at the rate of change. So to find the rate of change, I'll start off with the linear function in our table. It's going to be an easier one to do. What I'm going to think about is this is my x1 and x2. This is my y1 and y2. So to find my average rate of change, I'm going to take the y values and subtract them first, and then I'm going to take the x values and subtract them second. I'm going to write that as a fraction. Again, that's that rise over run. So I would do 2150 minus 1400, and I'm going to divide that by the difference between 20 and 10. Now using a calculator, what that is going to do is it's going to give me a rate of change of approximately 75. Now what 75 means is that this is gaining 75 new members every single day. So simplifying that out would give me 75. I'm going to compare that to my exponential function. So for the exponential function, I'm using my graph. So I'm going to have to estimate these points here. So at day 10, all right, it's a little bit beyond this halfway point. So if I were to count lines, we're going up by 300, so 300, 600, 900, so a smidge above, let's just say 950 for rounding purposes, and this one's a smidge above 1800, so let's say 1850, so it works out nice and pretty. So what we're going to do is the same thing we did for our linear function. So for the exponential, I'm going to take my y values, 1850 minus 950, and I'm going to subtract those two and compare those two with my days of 20 and 10. So subtract those two. And by simplifying that out using a calculator, that would give me an average rate of change of 90. So we will see then that by comparing those two, we would see that the exponential function is going to have the greater rate of change compared to the linear function. Again, what do these numbers mean? 75 and 90 is representing approximately how many members they gain each day from day 10 to day 20. So for website A, they're gaining about 75 new members every day. For website B, they're gaining 90 new members every day. All right, last part of this question then is wants to know, kind of compare who would have more members after 50 days. So we can see here right away that website B is gaining approximately 90 members every day between this time interval. The key thing that I think the best way to understand this question is understanding the difference between exponential and linear. A linear function that we see for website A is always going to go up by the same amount every day. So the 75 that we got would represent the number of people it gains every single day. So if I were to, say, start at 25 where I left off and continue to count to 50, I could figure out exactly how many people I would have after 50 days. But for an exponential function, remember that it grows, and that as it goes further and further on, it's going to grow faster and faster and faster. So we can already see that website B is gaining more members every single day, and because it's exponential, meaning it's going to grow at a faster rate, I know right away that website B should have more people after 50 days. Heck, I mean, right now at about 25 days, they're pretty close to where they're at now, and we can already see that this thing is going to start to grow at a more rapid rate. So again, Exponential functions, that growth compared to a linear function is going to be much greater because we're not increasing at a constant rate. So as we looked at throughout this lesson, again, we compared linear and exponential functions. I wanted to show some of the similarities, like that rate of change, like those starting values, okay? But for an exponential function, again, because we see that curve graph, that these things are going to be increasing or decreasing at a more drastic rate as time goes on, whereas a linear function is always going to be going up at a constant rate or down at a constant rate as we go on. All right, so if you guys got any questions, make sure you jot those questions down. Shoot myself, Miss Casper, an email. Otherwise, good luck on the Big Ideas assignment. Peace.